Hi everyone. Today we are going to discuss about navigation satellite and its communication system. Yeah, these are the contents. Introduction to satellite navigation, satellite and its orbits, GNSS, Global Navigation Satellite System, operating frequencies of satellites, data frame, modulation scheme, and transmission algorithm, and different navigation satellites what we have, and uh, Indian regional navigation satellite system and its application. So these are the contents regarding our topic. Yeah, satellite navigation. In short, we'll be calling it as an sat nav. So these navigation satellites are designed in such a way to provide us the latitude, longitude, and altitude of our particular position where we are, right? So as we are using in our mobiles the maps and the GPS receivers, where they are trying to take the values of latitude, longitude values from the satellite, and we will be getting the exact location, right? So this was started in 1960s by US military, and right now it was fully commercially we can see the navigation satellites. Yeah, coming towards the orbits around the earth for satellites. So actually, not only navigation satellites, we have the other different purpose of satellites. Some are for the purpose of maintaining the servers, and some purpose of the security purpose and all. So finally, what are the orbits we have to project our satellites, to locate our satellites, and the satellites can move in a particular orbit. Yeah, uh, in we have the most famous, the three most important orbits, where we will be calling it as LEO, MEO, and GEO in short. So LEO in the sense low Earth orbit, MEO in the sense medium Earth orbit, GEO in the sense geostationary Earth orbit. So these are the three different orbits, and which were located with a different distances from our Earth. Leo in the sense which is very shortest distance towards our Earth. Meo, which was like medium distance, and Geo in the sense most highest distance from the Earth. So what sort of satellites can be in which particular orbit, and what are the particular the speed and all? Let us see. Leo. Leo in the sense low Earth orbit. So actually, when we go with an low Earth orbit, which is all about like 300 to 1500 kilometers above the Earth, it means which is a smallest distance orbits. So in this orbit, if you are trying to keep a satellite and trying to make an orbit around the Earth, to rotate around the Earth, that particular satellite should be maintaining the speed of 5 miles per hour. It means 8 kilometers per second. So it's really and not a smallest issue over there. And surely if it is maintaining the same speed within a 90 minutes, it should rotate total Earth, means it should revolve around the Earth within a 90 minutes, right? So this is what the speed should be there when we are locating our projecting our satellite on the low Earth orbit. So most probably it comes to the issue regarding the weight of the satellite, what you are trying to project on the Leo, right? So this is all comes under the uh, when we are trying to project our satellite on the Leo orbit. And surely the operating frequency will be 1 gigahertz to 2.5 gigahertz will be maintained, right? Coming to the MEO, medium Earth orbit. So this here in medium Earth orbit, it is all about like 8,000 to 20,000 kilometers above the Earth. the orbit which can be when you are projected, and that when you are projecting your satellite on this MEO orbit. Yeah, we have many satellites in the MEO, medium earth orbit, so which can cover all about 12 hours to complete the total rotation around the earth, right? So even this frequency band could be 1.2 gigahertz to 1.6 gigahertz. So most of the cases we prefer to go with MEO in different application, right? Geostationary Earth orbit, GEO. So this is what the most flexible enough, but coming towards the distance from the Earth is all about 22,300 miles. It's all about 36,000 kilometers above the Earth. So this is the longest distance from the Earth. So here we call it as geostationary only because when this satellite will tries to rotate around the Earth will take all about 24 hours. So, guys, let us understand when a particular satellite is trying to project on our India, and it is trying to rotate around the Earth, and even the Earth is also tries to revolve itself uh, and comes to the position within 24 hours. The same thing happens to the satellite to rotate around the Earth also. So it means it is not going to change its position on which particular that satellite is trying to project. Means the projection towards the Earth will not be going to change. This the same will be there. So that is what means. It looks like it is a stationary orbit, right? So when the satellite at zero time it is showing on the India location, the same will be happen after completion of total rotation also. So it's look like exactly stationary. So that is what we call it as a geostationary orbit, right? So now the another one, when you are trying to locate the satellites in the geostationary, at that situation, surely to cover the total Earth, we need only three satellites. Three satellites is more than enough to cover the total, to navigate to total Earth orbit, right? Total Earth. So using only three satellites is more than enough when you are trying to locate in the from the geostationary orbit. So this is about geostationary orbit. Yeah, one more thing we have, which is same distance as it's like a geostationary only, but we'll be calling it as inclined geosynchronous orbit. The way of rotation will be different, right? So where in geostationary it tries to rotate around the Earth, here in geosynchronous it tries to rotate in eight design manner in inclination, right? It doesn't move around the Earth within the it's not within the altitude it tries to rotate, right, as an eight shape. So you can observe the way how it rotates around the inclination. So this is what geosynchronous orbit, right, guys? These are about the different satellite orbits in the around the globe. Now we are going to see what are the GNSS satellites we have. So actually, what we are using only GPS satellite. Apart from GPS satellite, we have also GLONASS, Galileo, and BEDO. So let us see here. You can see the global constellation satellites are GPS, which is designed by USA, GLONASS by Russian country, and Galileo by European countries, BEDO by China. So we have these four countries where giving us the global navigation systems. So even all these countries have their individual navigation satellites. They are trying to get the navigation values over all the globe, right? So we have another two countries which they are trying to navigate not towards total globe but towards their region or towards their country. Those are Japan and India. So we stay at fifth to sixth place, which we have our own navigation satellites. Apart from these countries, remaining all other countries tries to use the other country help to get the navigations. Even as India has their own Indian regional navigation satellites, but in commercial purpose, right now we in most of the cases we are using GPS satellites, but make sure within a short time maybe we are going to use the our own navigation satellites. Yeah, coming towards the positioning the satellite, guys, it is not that much easy to know the exact latitude and longitude values of what where we are staying, because when I open my mobile and when I check out where is my position, it's not that much easy to know my latitude longitude values with the help of direct satellite. Surely I require minimum 3 satellites values to get my exact value. And also I should come across the tropospheric ionospheric errors and time delay and the other noises. So if I come across all such errors, then only I can get exact latitude and longitude values where I am staying, right? So at that situation, I need also a spoofer which is trying to overcome all these errors and giving us the perfect value. So if you are having a GPS receiver in your gadget, surely it should come across the satellites and also a particular spoofer or some particular station which is trying to overcome all the errors and giving the exact latitude and longitude values. So what are the types of errors could be? It could be an ionospheric error, tropospheric error, satellite clock error, hemisphere data error, receiver quality, multipath errors, and dilution of precision error. So these are the types of errors we can come across while we are trying to take the latitude and longitude values. So if I want to position the particular calculation for the navigation system, so surely it come across all these errors. So if you go across the all the errors, you can, if you are trying to filter out these such errors, then only you are going to get the perfect value of latitude and longitude. To go and to do such things, a spoofer, what I said, we'll be calling it as SBAS station, which is called satellite based augmented station. So this augmentation station is trying to take the values of the all the satellites which they are trying to give some particular latitude and longitude values, and they'll be trying to match with other three more satellites, and they'll be trying to cross check, and they'll be trying to remove the errors of all the remaining tropospheric ionospheric errors which we have discussed. So all these errors will be filtered out, and they'll be trying to give us the perfect latitude and longitude values. Yeah, the receiver that supports SBAS means whatever the SBAS is trying to give, that will be taken by the receiver by what are the futures, means what makes us if we are take the values from SBAS. Yeah, you can see here it will be increasing the number of satellites used. So there may be a chance like the SBAS station is not only trying to take only one or two satellites help, it tries to say as many satellites where you are positioned, right? And it tries to filter out the exact value, right? It surely it is trying to reduce the ionospheric and tropospheric values, and of course the satellite clock error will be reduced. of course, like this SBAS station. In our India also we have one station which we will be calling it as an Gagan. Yeah. What are the frequency ranges? We have to operate, or like what are the frequency ranges which are running by these navigation satellites, which are communicating by this navigation satellites, which are trying to give some value. What is the frequency range they are following? So guys, you can see here, uh, down you can see the frequency ranges, which was like 3 kilohertz, 30 kilohertz, like that. So which was like started with very low frequency, which was 100 kilometers distance. It could be taking 30 kilohertz of frequency. Next, navigation purpose for all about 10 kilometers of distance, which is 30 kilohertz. And then slowly 1 kilometer, and to 100 meters, it's all about like something like radio stations, like that. um, there will be taking we will be having some sort of 3 megahertz. So guys, this is all about the wavelength, what I'm talking here, and the antenna size, what it means, like, right? So as if the antenna size decreases, surely the frequency range has to be increased, right? So the last but one, which is like after ultra high frequency, all about around the ultra high frequency, you can see the 3 gigahertz. So this is what around the 3 gigahertz of value, all about 1 to 40 kilohertz of uh, value frequency range will be using for satellite communication, right? So let us see what about the ranges particularly used by the satellites. Guys, these are the band, frequency range, total bandwidth, and general application for which particular application satellites will be using. So bands, you can see we have the microwave frequency bands like L, S, C, X, Ku, K, Ka. So for L band, we'll be using the range, the frequency range will be all about 1 to 2 gigahertz, which is a totally 1 gigahertz of bandwidth, which is used for mobile satellite services. Next, the S band is for 2 gigahertz to 4 gigahertz, all about bandwidth 2 gigahertz, which will be used for mobile satellite service and NASA also. Next, C band is for 4 gigahertz to 8 gigahertz. The bandwidth will be 4 gigahertz, used for fixed satellite services. And X band is from 8 gigahertz to 12.5 gigahertz, is all about 4.5 gigahertz, which is used for fixed satellite services for military and terrestrial earth exposures. And Ku band, same for military and of course used for broadcasting surfaces. And K and Ka band, which will be used for the same as like fixed satellite services and also broadcasting services. So the last one Ka is still 40 gigahertz, right? So these are the bands, frequency ranges, bandwidth, and application of different satellites, guys. But if you take about the navigation satellites particularly, this navigation satellites we are using 1 to 2 gigahertz. We are only using 1 gigahertz to 2 gigahertz of value. Let us see. As I said, we have multiple navigation satellites like uh, GPS, GLONASS, Galileo, BEDO, and our Indian satellites even. So which satellite is using which particular band, and which satellite is using what particular range? So guys, let me say, we have the band called L band, which is 1 gigahertz to 2 gigahertz. This is what used for the navigation satellites. So here, if you can see, the red color is for GLO, which is GLONASS. GAL is an Galileo, BDS in the sense BEDO, GPS, BDS, and IRNSS for the Indian. So actually, it was started about the L1 is all about here, if you can see, which is 1.5 gigahertz, right? So this was about the 1.5 gigahertz. It was started at here actually, and slowly the first GPS has taken, and at the same time again some part the Galileo European country has taken, and it is 1.75 gigahertz, and then slowly 1.61 gigahertz of BDO, which was China, and our Indian satellites is all about 1.1 gigahertz, 1.16 gigahertz. At the range of this particular frequency, our Indian regional navigation satellites are using this particular operating frequency, right? And also few GPS L5 band satellites, and also for a few Galileo satellites are also using the same frequency range, which is all about plus or minus 10 megahertz of bandwidth. Within this plus or minus 10 megahertz of bandwidth, all about like three different countries satellites are using this particular frequency range. Yeah, of course, you can see other different satellites are using different ranges. So guys, this is all about if the modulation technique has to be used, how these particular frequencies ranges with the help of this particular 1 gigahertz, 1.5, 1.6 gigahertz, the latitude and longitude value data from the navigation satellite has to be transmitted to the receiver or some base station where it is trying to filter it out and give the exact value. So we need some particular modulation technique and some particular transmission technique, right? So these L1 band is acting as a carrier frequency, right? So surely you are going to have. So here I'm just trying to say what are the requirements. So first, interface identification. For that, I need some GPS space segment, and there will be some user segment. So for that I am linking this L1 and L2, and then I'll be having to send the data, I'll be trying to use pseudo random noise uh, to make the giving the data, and adding some the uh, code to get the unique ID, right? So uh, along with this carrier frequency, the data, whatever the pseudo random noise, which is a precision, and along with this, we'll be trying to send the. It will be having some that particular satellite which having some unique ID, and along with this, we'll be trying to send the data. So this is the carrier signal, guys, which is L1 band 1.57 gigahertz, as I said. In other way, I can say 1575 megahertz, and L2 band is all about 1227 megahertz, right? So actually, for the satellite, we have the clock generator, atomic clock generator, all about 10 megahertz of clock generator. So what we do, this 10 megahertz of clock generator will be trying to multiply with 154 times, so that I will be getting L1 band carrier frequency, 120 times to get to generate L2 band, right? So to maintain the speed of 10 megabits per second. Yeah, this navigation data will have master frame, frame, and subframe. So in a master frame, we'll be having the frames, and in frame again, we'll be having subframe. So actually, the duration of one master frame will take 12 minutes to transmit. So actually, in one master frame, you will be having 25 frames, and each frame will take all about 1500 bits. So let us see So each frame again it has divided into 5 subframes, and each subframe again it takes at least 6 seconds for transmission and 30 bits of word, right? So let us see how these frames will be divided. So each subframe will be repeated for 1 to 3 frames, and 4 5 frames will have containing the navigation message, and 1 2 3 frames will be the same, and it takes total 25 frames. Fine. So it is formed like this. This is what the total data frame you can see here, guys. Yeah, this is what total data frame, guys. In one master frame you will be having 5 subframes, sorry, 5 frames. So this is what total one frame. In one frame you will be having total 5 subframes, right? So again, this subframe will having the individual pages. Fine. So like that, total 25 pages. Like that, you will be having total. This is first frame. Total to complete the master frame. This is how one particular master frame will be formed. So now this is how the transmission system will be. This is what your carrier L1 will be the carrier C by A, which is a pseudo random code, and this is what the data 50 hedges of data, system data, and the precision code, and L2 carrier. So combination of all these things will be transmitted by L1 and L2 signal towards the air. So for this, the modulation technique, we are going to use phase shift keying. Sorry, in most of the satellite navigation satellites, they are going to use phase shift keying. So phase shift keying, actually, apart from this, we have another types of modulation techniques like frequency modulation, amplitude modulation. Whereas those in as comparing to those things, here the data missing of data will be reduced, and we can have the perfect fastest transmission, right? So without any loss of data and without any uh, noise interference as comparing to the other modulation techniques, right? So in phase shift keying, what happens when binary values are transmitting? So when the data of 1 to 0 shifted, surely the 180 degrees to 90 degrees phase shift will be happen. So that is what we have named it as phase shift keying. So in this we have two types: binary phase shift keying and quadrature phase shift keying. In binary phase shift keying, what happens when the data over here, you can see the diagram. So if it is one, after one you will be getting again one, no phase shift will happen. But after one, the other value 0 comes, then surely 180 degrees phase shift will be happening, right? So this is how the binary phase shift keying will be going on. Next, what we have is quadrature phase shift. In quadrature phase shift, you'll be going with the 4 different phase shifts. So this is what the phase shift will happen. Now you can see here we are going with 90 degrees phase shift. So guys, the binary values here will be the combination of 2 bits, 00, 01, 10, and 11. So this is what how the diagram is trying to explain you. First, the phase shift will be taken with 2 different signals, I and Q. Then these two will be combined and transmitted. This is what QPSK. So in most of the cases, we use modulation, QPSK modulation technique in navigation satellites. Transmission technique. So in transmission technique, we have 3 different transmission techniques. Those are FDMA, TDMA, and CDMA. So frequency division multiplexing, time division multiplexing, and code division multiplexing. Guys, in frequency division multiplexing, what happens? The frequency will be divided and transmitted. In time division, frequency will be same, but time allotted for different systems, different way. In other CDMA, the frequency and time will not be divided. Only the code will be given for each satellite. So in most of the cases, CDMA is the best option for the transmission technique. And in most of the cases, for navigation satellites, also they try to prefer CDMA technique. Right? Yeah, this is where the difference between the CDMA and FDMA. Most of the satellites like GPS, Galileo, BEDO, IRNS, QUIZ, all these satellites will be using the CDMA only. Only GLONASS are using FDMA. So PNR code for the CDMA, it is means actually for each satellite it is having some particular identified number, right? So this is what for each satellite different PNR code is required. Whereas like in FDMA, one PNR code for all satellites. It's more than no need of pseudo random values there. And frequency, we are having only one frequency in CDMA, but whereas like in GLONASS, we'll be have to provide different frequency values for different satellites. Merits and demerits. So here the receiver will be more simpler enough. No interchannel biasing will happen, and no suspectable jamming will be happening. Means jamming will be happened in CDMA, but whereas like here the receiver complexity will be there, interchannel bypass problem will be there, but jamming less susceptible to be jamming. So this is what the different transmission techniques in our navigation satellite. So guys, in navigation satellites, this is what the most of the cases will be using monocular cameras. So for projecting means for checking out the navigation of the area. So guys, these are the different satellites we have. We can see the different satellites like here the first one, the system name BEDO, which was China's, Galileo for European, GLONASS is Russian, GPS is for United States, American satellites, NAVIC is the Indian satellites, QUIZ is Japan, QZSS is for Japan satellites, right? So the coverage, of course, the China, European, Russian, and USA, all these four countries are trying to cover total global, whereas India and Japan is trying to cover only regional, only up to their country area navigation. Coding, most of the cases I said, all are using CDMA only, only GLONASS, Russian country, they are trying to use both FDMA and CDMA. The altitude, as I said, all are using geostationary. It means will be more than 20,000 kilometers. All the orbits will be more than 20,000 kilometers. But the surely the orbit, the kilometer distance should be compulsory more than 100 to 50 kilometers distance should be maintained, because like one satellite has to not to collide with another satellite. Most probably the orbit will be maintained in such a way. So anyway, all are more than 20,000 kilometers above. Only the Russian satellite, which is all about 19,130 kilometers. And the satellites, all about the China has 28 satellites right now. In 24 satellites in MEO orbit, 3 satellites in geosynchronous orbit, 1 is in geostationary orbit. In Galileo, European country Galileo satellites, 26 are in orbit. Out of 22 are in operational. Means only 22 are in working and 6 to be launched. Coming to the GLONASS, which is Russian satellites, 24 were designed, all 24 are in operational, means they are working, and one is in testing. And GPS, total 30 satellites we have, GPS satellites. Of course, even I think working all about like actually 28 to 30 satellites, they are in working condition. Now coming to the IRNS, Indian satellites, we have total 8 satellites. Out of 3 are in geostationary, 5 are in geosynchronous. And yeah, guys, in Japan, we have total only 4 operational satellites. 3 are in geosynchronous and one is geo stationary orbit. Right, total 7 in future they are planning more satellites. So, like guys, this is about the navigation satellites, different satellites and their orbits and their uh, modulation techniques and transmission techniques. In the next video, I'll try to give more information only about Indian navigation satellites, and I'll be trying to give some more information about IRNSS, Indian navigation satellites. Right, guys, thank you. If you have any doubts or anything to give the suggestions, please give it in the comment box. Thank you.